so far we kind of lay out all the backgrounds that we have to know before we understand it. So we're gonna talk about differentiability and derivative. Oh, by the way, before we do that, we have to talk about partial derivative. And higher order derivative. Okay, so let's start from the partial derivative. So how do we define partial derivative? So let's say so from now, for a short period of time, I'm gonna talk about only two variable functions, and then we can see how it's generalized to several variable functions. So when you talk about partial derivative, you have to have a function, two variable function, and a point in the domain of that function. So this is the point, x comma y, x0 comma y0. It's a specific point. So the definition of partial derivative in terms of x is the limit of this ratio. So there are two parts whenever you get the concept here. First, you have to remember the definition. Okay, so you have to practice yourself so the definition comes out naturally. And second, don't just remember remember the formula. Think about the meaning of what it is about. I'm sorry, so this is not x. So this is t. So let me write it again. So we have x0 plus t y0 minus f0 y0. So by the definition, it means that basically it's the meaning, right? So if you know the meaning, then you can write the definition in different format. So let me write it in different way. So instead of t goes to 0, I can let x goes to x0, and the denominator is x minus x0, and the numerator is fx comma y0, fx0 y0. So you have to understand what is going on. So you are talking about the limit of ratio, and this ratio is between the value of function and the value of x. So here t is only governs the value of x, right? So actually the t comes from the difference between value of x from x0 plus t and x0. And here the same. We already have the difference between the value of x and x0 in the denominator. So it's a ratio between the value of function and the value of x. And what is the meaning of x? Why do we choose x? Because that's the variable that we are changing the value of the domain. So we are not looking at the fixed value, we're changing the value of x coordinate, so which means that we are moving my points from x0, y0. So and then when I do that, I want to see the ratio, the limit of the ratio. So basically I want to see how the function changes when I move my point from x0 to y0 only by changing x coordinate. In other words, moving the x coordinates or moving along the x-axis. So if you use the same meaning as a single variable function, this is the rate of change of function in terms of x. Rate of change of function when you move your point along the x-axis. So basically not really x-axis, the horizontal line, right? So once you know the definition, you can see why this has to be defined this way. So let me use the second way of writing the definition of the partial derivative in terms of y. Y minus y0 and fx 0 y minus fx 0, y 0. Okay? So you do the same thing. I want to see how fast the function changes when I move my point in the vertical direction from y 0. So these two follows actually from the higher concept. It's about the directional derivative. So you don't have to move your point in x or y direction, right? So you can move in any direction. So it's a directional derivative. We're gonna come to that part later. So let's talk about the differentiability for now. So the definition of differentiability of two variable function is the following. First, we need to define the linear approximation. So let's say Lxy to be, I can write up to here. So f of x, x0, y0, x minus x0, and fy, x0, y0. Y minus y0. So you can see that everything is a number except x and y, and x and y have only degree of 1. So it's a linear formula. So polynomial degree 1. And f is differentiable at x0, y0 if you take the limit of this x minus x0 squared, y minus y0 squared, and you take the difference between f of xy and Lxy, then it has to be 0. So if this is true, the limit is 0, then f is called differentiable at x0, y0. So the differentiability is not about the function only, it's about function and the point. We always have to say function is differentiable at certain point. But when you say without mentioning the specific point, it kind of means that the function is differentiable at every point in its domain. But it also implies that this happens for every point. So this is something you have to remember first. So there are two things, the linear map, L, and the limit. Actually, it's not just the limit, it's an equation of the limit, right? So what about the L? Look at L carefully. So you have a partial derivative as a factor or coefficient. So you need to have a partial derivative. The partial derivative is not just comes free. Something you need to have. This is limit. So sometimes the limit doesn't exist. So differentiability kind of assumes that you have a partial derivative or partial differentials of the function at that point for x and y at the same time. And therefore also, it also requires that the function is well defined at that point, of course. And once you have L, then what does this limit equation says? It says the limit is 0. So what is this limit? It's a ratio of two things. What's the numerator? It's a difference of value of functions. What's the denominator? It's a distance between the point x and y to x0, y0. So x0, y0 is fixed point, and x and y is some point nearby. So when you take the limit, you take that xy closer and closer to x0, y0. So your distance goes to 0. So however, even though the distance goes to 0, the denominator goes to 0, you want the limit to be 0. That means your numerator must go 0 faster than the denominator. Which means that this equation says the value of function value of functions of f and L approaches together. The difference between the value of these two functions gets to 0 much faster than the speed of the point approaching to this x0, y0. So you can say that what we are doing in this L business is that Lx is, it's called, actually the name is a linear approximation of xy and at x0, y0. So having said so, the limit equation says that the linear approximation is getting better and better. The approximation always has an error, but you see the numerator is an error, right? Because it's the difference between the true value and the approximate value. The error goes to 0, but the error actually goes way faster to 0 than the distance between these 2 points goes to 0, right? So in other words, this equation says that this linear equation, linear approximation, is a good approximation, right? So you can see from this single variable case, when this linear approximation is not a good approximation. So see, you know, everyone knows that this y equals to absolute value of x is not differentiable at 0, right? Why is that? We often say a slope has, you know, -1 and 1, and it's not always one slope. Well, kind of right, but it means that according to that definition, whenever you say differentiability at some point, whenever you say a function is not differentiable at some point, it always means that there is no good approximation. So let's say I take this line. So when you say approximation, it has to be the line passing through that point, because at the center, the error must be 0. So if you take this line, or the formula whose graph is this line, as a linear approximation, the error is 0 on this side, but error on the left-hand side is large, but the error large doesn't mean always that it's not differentiability. The not differentiable because the error is decreasing at the same speed as x approaches to 0, because it's linear, right? You can compare this equation as this one and this one. So this is y equals to x squared. So if you take the linear approximation at 0 as the horizontal line x-axis, then you can see the error is here. I'm not saying the error is 0. The error must be there, but the error is decreasing much faster than the speed x goes to 0. So because you can see that it's a parabola. But here it's linear, so the error is approaching to the same speed. Therefore, the limit is not 0. So why am I talking about this single variable case when I talk about this second variable, 2 variable case? Because we can just simply enlarge this, generalize this situation into 2 variable case. So think about that. Now our picture is now this is z axis, and this somehow give you x and y axis here. And let's say we take a rotated picture of this. Then this is a cone, and this is the what's it called, the paraboloid. So this is the graph of x squared plus y squared square root, and this is the graph of the same thing happens here. But this is, let's say, x and y, and this is z. So this is the graph of that equals to x squared plus y squared. So when you talk about the origin, 0, 0, which is both are in the domain of the functions, square root of x squared plus y squared and x squared plus y squared, this point is not the point, the function is not differentiable at this point, but the function here is differentiable at this point. Why? So let's think about the linear map here, linear approximation. Now it's a 2 variable function, so we have to find this coefficient. First, the value of function is both 0, so nothing there. But what is the partial derivative f of x and f of y at the origin? So here, we cannot take the partial derivative, but we can guess what that is, but there's no. So here, let's start from here. What's the partial derivative of this function of at 0, 0 of x and y? So when you move, so again, giving you the definition, but also the meaning, without giving you the answer here, is that when you move away from the origin in x direction, you have to see how fast the function is changing. So having a fast or having the rate of change means that you want to see the slope. So basically you cut the graph into the slice, into a slice which is parallel to x-axis here, you get this kind of a section, right? When you cut the graph with a knife, which is parallel and passing through the origin, you get the section of the graph. And you're looking at the ratio when x goes to x0, which is 0 here. So that means you want to see the slope of this line. So we can see actually the paraboloid, right? So parabola in the x set plane, right? So f of x, 0, 0 is 0. And you do the same thing for when you take the partial derivative in terms of y. You cut the section. You cut the section parallel to y-axis, passing through the origin. See the section, which is the parabola, and you take the slope to get the ratio, rate of change. So you can see that the slope is always also 0. So f of y, 0, 0 is also 0. So what happens to the L? In this case, when you take the linear approximation at the origin, it's 0. Everything is 0. So x minus x0, y minus y0 has a coefficient 0, so everything is 0. So when L xy is just 0, it's a 0 function. What I'm saying is it's a 0 function. So z value is 0. No matter what your x and y is, the graph of that kind of function is a flat surface, flat plane, which is actually the same as xy plane. So this flat plane, xy plane, is the linear approximation, graph of the linear approximation. When I say differentiability, I want to see the error rate, I mean the rate of error that goes to 0, how fast does the error goes. So I want to see how fast does the error go. But this is symmetric picture, so it doesn't matter whether you come from the 45-degree angle or 0-degree angle. So you only want to see from one side and then how fast the error decreases. So this is exactly the same as this line here. So line is decreasing, not in the same rate, but much faster rate to 0 than the point approaching to the origin. But here, you don't have f of x 0, 0. You don't have this. There's nothing here. There's no number that matches to the definition of the partial derivative. Why? So think about it again. So when you talk about the partial derivative in terms of x, of this function, square root of x squared plus y squared, you're talking about when y equals to 0, so y is fixed to 0. So when you take the square root of x squared, it's an absolute value of x, right? Exactly the same graph that I have drawn before. So when I cut the section, that's the graph of x absolute value. There's no slope. There's no tangent slope, right? And also, as I said, the reason why we don't have differentiability here is because the error rate doesn't go to 0 in a higher speed. So there's nothing here, and it's the same reason, and symmetricity says there's no partial derivative. Well, in that case, I cannot even define the linear approximation because that's what it needs. These two are needed, right? You cannot say the linear approximation is possible. But let's say, okay, so just the name by itself, linear approximation is something linear, so I can just randomly choose a linear map, which gives the graph of a plane that passing through the origin, and then claim that this might be a linear approximation. So let's say use the same xy plane, which is L equals to 0. So as my linear approximation, ignoring the definition here. Then what happens? I get the error rate of this linear approximation, which is the difference between the value of function and the linear approximation, goes 0 at the same speed of the point going to 0. So that's not what the differentiability, this equation says. The equation says that it must go, the error rate has to go 0 much faster than the rate of the point approaching to the given point. So this function is not differentiable at 0. That function is differentiable. So by looking at the picture itself, you can see that this is kind of pointy, and this is smooth, right? Round and smooth. So you can say the differentiability is kind of giving you a graph which is smooth at that point, but that's not always true also. But there are lots of counterexamples you can think of if I go deeply, if I go deeper, but I don't want to because I have something to cover. So, so we covered this too, but let me generalize and make a table of these two concepts here. So partial derivative the situation is same for several variable function, multivariable function. First, let me start from the notation here. So as I said, if I have f of x and y, then I can say it's a partial derivative of f of x, x0, y0. Oh, sorry. So I have to be careful about the wording here. So first, I want to make a rigorous use of this wording, differential. Okay. So when I talk about this two variable function, I can denote f of x as y, or I can write del f del x, x0, y0. And sometimes we use del x, x0, y0, f. So these are all same notation. I mean, same partial derivative, different notation. Okay. So y is the same thing. So now I can generalize to the three variable function. Let's generalize to the several variable function. So let's say when I talk about the several variable function, I will use x1 to xn as an independent variable, but using the same function notations f. In that case, what I say f of x1, let's say f of x1, x1, 0 up to xn 0. So 0 doesn't mean that it's a power, it's just another index that represents that it's not a variable, it's a number. Or let's not use x anymore, so just make sure that it's a number, and may use a1 so that it's just a number. So this is a number, specific number. Okay. So how does it define? So again, it's the same way. So we only want to change that variable, leaving other variables same as it is, as this constant. So if I use t, then t is the factor that changes the value of that variable. So here I'm using the values in the I1, the first variable in the function. So I'm taking a1, a1 and make a slight change by t, and then keep the rest not changed. And then I'm looking at the difference, remember? So I'm taking the original value of function at that point. I'm looking at the ratio. Okay. So that's for x1, but as I said, you can write differently. So we can say x1 is going to a1, and you can take the ratio between x1 and a1, and the difference between fx1, a2, an, and fa1, an. Okay? The same thing. So you don't see anything different, right? So as I said, the earlier here. So that's for x1. I'm sure you can generalize to the partial derivative of xi for general index I. There are another notation, the same way we did it here. So you can write your partial differentials this way, or del f del x1 a1 an, or you can say del x1 a1 an f. So these notation symbols are useful in some contexts, so we can. I'm going to interchange these symbols many times without mentioning every time that this is the same partial derivative. So that's a partial differential, okay? Yeah, so sometimes I exchange the wording differential and the derivative, but the differential and derivative is different. So differential, so here, differential is a number, it's a value. Okay? So when you talk about derivative, of course, it's not strict sense, but in our, because we are learning for the first time, we have to be careful about using of this wording. The derivative is a function. So when you say derivative of a two-variable function, f of x and y, then it's a function whose values are differentials. So here's the definition. It's not very special, but so this is a two-variable function whose values are at x, y of is, the value at x, y is the partial derivative at that point. Okay, so and maybe you can put it x0, y0 and make sure that this is the specific value. Okay. So for example, let's say f of y equals to x squared plus y squared. I want to find out f of x as a function. So that means I need to know what the differentials is for arbitrary point, right? So let's go for the definition, and then I'll tell you the trick here. So I think I mentioned before, but so the definition is that when x goes to x0, I'm taking the ratio between these two numbers, f of x, y0, and f of x0, y0. So let's plug that in. So y0, y0 cancels out each other, so all I have is just x squared and x0 squared on the numerator, and the denominator I have x minus x squared. Right? So I'm just plugging this formula in here, so y0 cancels out. So what happens here? So it's a limit of x0 plus x0, which will factor out this. So when, x plus x0. So that's 2x0, right? So now, when I choose x0, y0, I can choose an arbitrary number because the function defined on every xy plane. So instead of using x0, y0, I can just replace it as x and y. So therefore, I can say fx, xy is equal to just 2x. So if you're looking at 2x, it's just another formula of two-variable function. Just y variable is missing in the formula. So this is another two-variable function. And you can see the same thing when it happens. It happens when you take the partial derivative in terms of y, it's 2y. So you can take this, you can obtain this formula simply by looking at this formula and then consider the other variable as a constant. So this is the result obtained by taking derivative. So let me write taking derivative of the original function f, considering other variable as constant. Okay? So where does 2x come from? We consider y, which is other variable, because our focus is on x. We take y as a constant. Then when you take so your formula is just nothing but a single variable function formula. So we can take the derivative in that variable, and y disappear because that's a constant. So it's 2x, and same for 2y. Okay. But again, I don't want to stress this out. I mean, I don't want to emphasize this, because you can always find the formula. I mean, that's not even something that you have to work on. It's not a practice at all. I mean, if you want, the more important thing is you have to understand the meaning of this. Okay? So when you say this formula, this kind of notation, this is about a function, not a value, and so on. Any questions? Any questions? Okay, so it's about multivariable function, and there are other type of multivariable functions. So far, we only talk about the function whose value is a number, right? So 2-variable function, 3-variable function. It's about value of function which is equals to number. But now, let's think about this case. We have f x y. So let's say I usually write it this way. So f u v goes to x y. So that's another type of multivariable function, which is the simplest type I can think of, which is it has more than one independent variable, the output variables, right? So this function tells you that there is a point in UV plane, let's say u, v here, and there is a map. So map is nothing but assignment, the rule of assignment that maps the one point to another, one value to another. So it maps to a point in xy plane. So of course there is entire points, but I'm just looking at the two specific points. And I want to do something about this, right? So the best way to understand this function is just split out all the output variables. Don't think about x and y at the same time. Of course, it's sometimes important, but here, if you know the behavior of x and behavior of y, then you can know, just combine this together to see the behavior of point x and y. Just so you can say f1 is the value x, something that corresponds to whose value corresponds to x, and this is one function, which is real valued function, whose two variables is independent variables, and y is the value of function, second function f2, whose value is dependent, whose value is determined by u and v. So you just do it separately. So what we want is just the same definition here. We want to see the differentiability. So what did I say about the differentiability of these two kind of functions? There's the same kind of function. So it's differentiable at a certain point if the difference of value of function is changing smoothly. So in other words, the linear approximation is a good approximation. So if these two are differentiable, if these two functions are differentiable at certain point, at the same point, then we say the function is differentiable. So this is the most important, most simplest definition I can give you here. So this f is differentiable again, every time you say differentiable, it's about a specific point. So now our domain is UV plane, so I'm going to give the point as U0, Y0. If this F1 and F2 are at the same time differentiable at the same point. Okay? So now, what can we say about the differentiability of the more general function? So let's write here about the general definition of differentiability. So let's say we have x1 up to xn as an independent variable, which is input variable, and y1 to ym as an output variable. Sometimes I interchange n and n, but just understand that this is in context. So we have m different functions, m real valued function that determines each output variables. So let's say y1 is f1 x1 up to xn. So y1 is determined by the formula of f1, and y2 and ym is determined by the formula function f m. Xn. And when you want to say the function is differentiable, you have to say about this differentiability of this function. So how do you define the differentiability of these two functions? So let me just leave it here and then come back here. So I'll give you with the example. So here, let's say x is u squared plus v squared, and y is uv. Okay, just it really the formula doesn't mean anything here, but just make sure that we are dealing with a specific function. So we are looking at the two variable function. We know what the differentiability means. We have linear equations, linear approximation, that the linear approximation satisfies some limit equation. So this differentiability is equivalent to say that this f is diff if for I from 1 to 2 we have let's see, p plus t goes to 0, t, and f. So the rest of the values are fixed as either u0 or v0, but the I part, so when you have I1 or Y2, well, let me do it one by one. So since we are looking at the uv instead of x1, x2, so for u, so I don't want to change notation. If so, here f of u comma v0 minus f uv minus L L1 uv and u minus u0 square v minus v0 square equals to 0, and uv goes to u0 v0. So that's the differentiability of F1, right? Just read the notes. Read the thing that you take the note before, right? So we are talking about the differentiability. And not just this one, we need the same thing for F2. Okay? So if these two happens, if these two are same, then we have F is, we say F is differentiable. So let's combine this. Let's combine this together into one single equation. Because we have the same limit, both uv goes to u0, v0, and we have the same denominator. The only thing we need to do is just combine somehow the numerator. So let's do that. So how do we combine these two? So you can consider this ratio and that ratio as a coefficient of a pair of numbers. So just take these two as elements in the pairs. Just take a pair of these numbers. Okay? So what I want is limit of, let's see, this thing. So I'm not going to write this everything into pairs, and the limit is the same thing. And what do we requires here? So we assume that the limit is affecting this coordinate and that coordinate, and the result must be both 0. So we want this to be goes to 0, 0. So if I really want to try just to combine these two, I can't do this, right? So and then now we have to make sure is this notation make sense. So when I take the limit of these pairs, what am I looking at? I'm looking at somehow a point, right? Two-dimensional point. So I can say, oh, maybe if I make uv point too close and closer to u0, v0, I want to see how these 2 points, whose coordinates are given this way, approaches to the origin, right? So that's the one way you can easily find. But then I want to get rid of this common denominator. I mean, not get rid of, I just want to make sure that this is make a clean statement here. So if I take the point at these pairs as a point, then I cannot multiply, I cannot make this numerator as a factor of outside of these pairs. So instead of looking at this as a coordinates of a point, let's look at this as a coordinate of vectors. So instead of points, when I take a pairs of numbers, I can also do it with a vector. Right? So in that sense, I want to see the vector goes to the 0 vector, right? So the one then I can make this 1 over square root of thing goes outside of this. So I can say this thing 1 over the square root. You see what I'm doing here? I'm not going to write everything this time. So the square root part is this. Okay. And let's try to do more clever thing here. So since we have now working with the vectors, so the denominator is now fixed. That's that formula. And the numerator, you see that we are taking something out of something. So we're taking F1 and F2 as F1 and F2 as the first factor we have. And what we want is take out this value of L1 and L2. Right? That's what we have. That's what we wanted to have. The first coordinate is F1 minus L1, and the second coordinate is F2 minus L2. So that's what we are doing here. So now looking at this F1, F2, that's exactly the function f, right? Although the value is not given as a vector, but the the information itself is just a pair of numbers. The values are f1 and f2, which is the value of x and y, which is the value of function f. So we can say that this is f, and now look at this one. I'm going to write down one by one. So f1 u0 y0 plus f1 x0 y0 x minus x0 plus f1, so that's L1, so I'm just writing L1 formula here, y minus y0, and there is a formula of f2, L2, f2 u0 y0, and so on. So I'm not write it here. Rest of the things left is blank here. That's the numerator, right? So that's the numerator, and there's the denominator and the limit. But then, look at these two. So what we are taking off from f, the formula, is first we take the value of the function f1 and f2 at the specific point right here. So let me write up to here. Maybe. Okay. So then I can do this. So instead of having these long expressions, let's break it down into simple ones. So here, f1, f2 is now becoming fuv, but because this is just a formula, this is not about u0, v0, right? Remember, u0, it's not about u0, it's a uv, right? So it's a here, uv. And then if you take these two, then what? f1, f2 value combined together at the specific point, u0, v0, that's the value of function at u0, v0. Okay? So and then, think about this. f1, x, x0, y0, x minus x0, plus f1, y, x0, y0, y minus y0. That's the first coordinate. And second coordinate, f2, x, x0, y0, x minus x0, f2, y, x0, y0, y minus y0. Here, so this is the numerator. Of course, don't forget this. So there is a square root up above, below. So can you make this two-dimensional vector into simpler form? So there's something common in between, right? So there are x minus 1, x minus x0, and y minus y0. There's something common. So coming back here, how do you make two? So what we have in common is x minus x0, y minus y0, right? So I made it as a 2 by 1 matrix, because 2 by 1 matrix is nothing but two-dimensional vector. And in order to make two-dimensional vector like this, what I need to do is multiply the partial derivative. There are 4 different partial derivatives, right? And these are all different partial derivatives of each other. So let's say we want to make the first formula. So I want to multiply this to here, this to here. So if I take that, make it into a matrix multiplication, so that means the first row has to be the first formula here. So one that I have to multiply with x minus x0 is something that goes in the first row, first column. So this is f1x, right? So I omit x0, y0. Right? So actually it's a u0, y0. So excuse me here. So anyway, so let's omit this notation here for simplicity. And what is multiplied to y minus y0? It's f1y. F1y, right? So that's the first coordinate. right? When you do the matrix multiplication. And what's the second coordinate? That's something that you have to go after multiplication, goes to on the second row. So has to be F2x, F2y, right? So when you do the multiplication, this is 2 by 2, this is 2 by 1, you get 2 by 1 matrix, which is two-dimensional vector. So you just expand it to the two-variable function. Then you get the same idea here. And you can make UV, F, U0, V0, and take the multiple, take the subtraction here. You can make your numerator as simple as this. So here, now we are changing the view of its function values from as a point to as a 2 by 1 matrix. Because here in the beginning, I said, okay, so the pair of points at whose values F1 and F2 can be given as the vector. So that's why I use this just F without mentioning the vector notation. But here, since after all we want to take a subtraction between these value, whatever that is, to X, a 2 by 1 matrix, I'm looking at this value and this value as 2 by 1 matrix. But the notation is not important. All I want is just having the computation done in the same way we defined earlier with this definition. So I want to subtract these two, right? So if I make this 2 by 1 matrix, 2 by 1 matrix, everything is okay. So everything, it will be just same computation as before. So in the denominator, it's the same. It's always the same. Nothing changed here. So what I want is, after all, we combine these two limits into one limit. And what do we want on the right-hand side? We want the numerator to be just 0 matrix. Just 0 matrix. So let's put a 0 dot bold 0. So it's not a number anymore. It's just a 2 by 1 0 matrix. So now, what do we say about the derivative? So actually, we haven't talked about the derivative yet. We have talked about the partial derivative, right? Partial derivative as a function whose variables are 2 or 3 or n. But we never talked about the derivative itself. Derivative. What is derivative here? So we have a value of function, specific value of function, and something multiplied with the difference of the point. So here it's a difference of a vector as a vector between the point xy and x0, y0. Sorry, it's not x, it's u, v, so you have to keep making mistake here. So u minus u0, v minus v0. So the derivative is this part. This is the derivative. So this whole equation is coming from the definition of differentiability, and by the differentiability, we guarantee that this 2 by 2 matrix makes this equation true, right? So the definition of derivative of the function f is the 2 by 2 matrix. So in this function, let me make it sure that so that you don't confuse with other function. This specific function, derivative at u0, v0 is 2 by 2 matrix f of 1 x u0 y v0. The next f1 y u0 v0 f2 x u0 v0 f2 y u0 v0. That's your derivative. Just remember definition. Your derivative is a matrix, and since it's 2 by 2 to 2 function, the size of that derivative as a matrix is 2 by 2. And you have to remember, just first, if this is the first time seeing kind of derivative as a matrix, just remember the index carefully. So the first row has the same function. So first row has same f1 functions to take partial derivative. And if you change the column, you're changing the variable that you're taking partial derivative with. The first column, it has the first variable of your function. Sorry, it's not x. Make mistakes here. It's u. So u. So it's u, v. Okay. So column changes the variable you're taking derivative with. Row changes the function. Okay. So since there are two output variables, because that's why we have two rows. Because we have two independent variable input variables, we have two columns. Okay. So going back to our definition here, what's the derivative of this function? Let's say the notation, the derivative of this function at 1, 2. Okay, u0, v0 is 1, 2. What is it? So you first want to take the partial derivative of u squared plus v squared in terms of u, and then you want to find the differential at 1, 2. So usually you have to find the differential first before you find the derivative, but we know what the derivative is by using the trick. So we can find the derivative first by taking v as almost constant, so it's just u squared. So taking the derivative of u squared in terms of u, you get 2u, right? So 2u means u equals to 1, you have 2. And look at the second column here. You take the derivative in terms of v. Now u is constant, so it's 2v. So v is 2, so therefore it's 4. And how about the second formula? We have u times v. Now, when you take the partial derivative in terms of u, I said v is considered as constant, but it's about just u times some constant. So when you take the derivative, you can just have a v, which is the coefficient of u. So when v is 2, it's 2 again. And the last one, so uv in terms of the partial derivative of uv in terms of v, you get just u, right? Because u is constant. U is 1. So that's your derivative. Derivative, so it's derivative at 1, 2. So, so in strict sense, it's not derivative, it's differential, so it's a differential. So differential of the function. Okay. So let's talk about this in a general sense. Differentiability and the differential. So this function is differential at a1 up to an if we give. If means it's not conditional, it's just sufficient and necessary conditions, because we're talking if inside of the definition statement. So if all this are differentiable at a to an. Okay, that's the differentiability of a general function, general multivariable function. So then, now we immediately goes to the differential. What is differential? So whenever you say differentiability, you need automatically what is differential, because having differential is equivalent to have differentiable. Okay? So in this case, your differential of the function f at let me write a as the collection of these coordinates a1 to an. For example, notation wise, I'm gonna use a arrow here. You can think of this as a vector, but I'm not really meant to use it as a vector. I would use it as a boldface A, but I cannot make it distinguished, so I just use the arrow sign here. So this is arrow, sorry, so this is a kind of arrow, okay. I made a head to be. So anyway, sorry, so this is the one notation, but sometimes I also use this way. I think this is more common, DFA. So this kind of yeah. I mean, this is not a good notation. This is kind of I don't know why I use this, but I usually don't use this because it kind of confuse you with the directional derivative. So this is better notation. So the differential of a function at the point A is denoted by this, and this is what? Matrix. Again, it's a matrix. And entries of this matrix are partial derivative of these functions. So again, the same principle applies. Each row has the same function. Each column has the same variable. So F1, all the way up to Fm. Okay? And then we're taking partial derivative of each variable from x1 to xn. So first column x1, last column xn. First column xn, last column xn. x1 and xn, sorry. And the rest we can fill that out. And these coefficients, these entries are not formula. These are partial differential, not partial derivative. So you have to take the partial differential at the point A, given point. So this is your differential. So why is this differential required? Because whenever you say differentiability, meaning that these functions are differentiable, if you combine these limits, there are m number of limit equations into single limit equation, then what it looks like is that something like this. So you want to make your point x goes to A, and you want to see how the rate of change is, how fast the function is approaching to the linear approximation. So you want to see the distance between the point x and A. This is x. And that's the denominator. So I said this is the norm, kind of a norm, because norm has the same formula as the distance between the point of x and A here. And the numerator, look at this. So what we had, we erased it. So what we had is the original value of function f, and then subtract the value of the function at that specific point. And we have this matrix, B, F, A, times what? The difference between x and A. So here, you have to be careful about interpreting the notation here. So we have matrix here, and multiplying with the vector. So this vector is not a vector represented as a bracket. It's a n by one matrix. So this matrix is m by n matrix. Okay, so this matrix is m by n, and this is n by 1 matrix. So when you take the multiplication, you get m by 1 matrix, which has the same number of rows as the number of output variables. So here, these values, the value of functions, are not just a single number. It consists of m values. So these values are also considered an m by 1 matrix. So you see this addition or subtraction is about m by 1 matrix on the numerator. So what we want is this whole thing goes to 0 matrix. Every entry goes to 0. That's the definition of differentiability of the multivariable function. So I'm going to give you some examples because conceptually you have to understand. I mean, there's more thing you have to memorize than understand right now. But first, memorize all this. Memorize the formula, memorize the definition. Then I can give you some examples that you can check whether you understand it better. But let's give us a typical example here. So here, x, y, to x plus y, okay, so y plus 2 and x plus 2x plus 3y. Okay. So it's a 2 to 3 function. So it sends two-dimensional point to three-dimensional point. So I want to see the derivative. Or differential, sorry, it was differential. I want to see the differential of this function. So before we even start any calculation, just count the number of dependent and independent variables. So what's the size of the differential? How many rows, how many columns? Row, how many rows? Count the rows by number of the functions, right? How many functions do you have? 3, yes. So it's gonna be 3 rows. And how many columns? 2. So it's going to be 3 by 2 matrix. So first row, our first column, okay. So F1, F2, F3. So F1 partial derivative with x. So you take partial derivative of x plus y in terms of x. What is that? 1. Okay. Just consider y as constant. And here, let's say here. So first function x plus y. No, second function, sorry. Y plus 2, take partial derivative in terms of x. What is it? 0, because there's no x, just a constant. Then how about the third column? It's our third row here. Third function, partial derivative in terms of x. 2, yeah, 2. So you can do the same thing. So here, you're taking partial derivative in terms of y only, so 1, 1, 3. Really doesn't matter what the point is, right? We don't use this 1, 1 here, right? It's only because we have linear equations for every formula, right? I think I just covered the first video I uploaded here. So there's one thing I want to emphasize and then finish the lecture today. What's the meaning of the differential here? That's the most important part. So this is probably, that's what I wanted to emphasize in the entire course. I mean, if you understand the meaning of the differential properly, you can forget everything else, because you can start over. But, so I'm saying that this is the foundational concept of the calculus or any other mathematical tools. So think about the meaning of the differential. So in the video, I started with the meaning of the differentials in the single variable function and tried to generalize these. But let's start from right away here. What this function does, what does this function do? So it sends a point in x and y plane into, let's say, although these x and y are different, let's just name it the same symbols, x and y and z here. So when I change x comma y, let's say 1 comma 1, okay, if I change the point x and y from 1 comma 1, then originally where was it? It was 2, 3, 5, right? 2, 3, 5, maybe here. 2, 3, 5, right? So if I move certain this direction, maybe this will change some direction here, right? So just giving the final, just the answer directly here. This differential determines the instant movement of the output space by the input space, by the movement of input space. So I'm saying again. So differential determines the movement of the codomain space or output space according to the movement of input space or domain space. So what does that mean? So if I really want to see the actual values, actual position of the point, when I move my point in the domain, you have to compute the formula of the function. But that's the best way you can do it. Just giving the exact answer, right? But what does differential do? Differential kind of approximate the instant movement. So in other words, you're about to start into certain direction from your domain space at certain point, and you want to just estimate how fast or in what direction your point in the codomain space is starting to moving. So if I say I'm moving in direction of, so now it's direction, so I can use the vector notation 0, 1, okay? From 1, 1, since I know that the differential at 1, 1 is this, I can estimate the instant movement of the codomain space from 2, 3, 5 points, which is given by V as the following. So we have 1, 1, 0, 1, 2, 3 times the vector movement 0, 1. So it's a two-dimensional vector. I'm changing to 2 by 1 matrix, okay? Not changing the order of the variables. So when I'm taking matrix multiplication, what do I have? It's 2 by 3 matrix times 3 by 2 matrix times 2 by 1 matrix. I get 3 by 1 matrix, which is 3-dimensional vector. Let's do the matrix multiplication. So first entry 1, 1, 0, 1 is 1, and 0, 1, 0, 1, 1, and 2, 3, 0, 1, 3. So what does that say? What does that mean? V is a vector with coordinates 1, 1, 3. It's 1, 1, 3. So in this example, I can say that if point is moving in direction of 0, 1 from 1, 1 instantly, so it's about to start moving in that direction with that speed, then the corresponding point in the codomain space, 2, 3, 5, is about to move in the direction of and speed of 1, 1, 3. Make sense? Okay, so why is it useful? Why are we doing this? So sometimes, so in this case, so function is so simple, you can just plug in the numbers and compute. Sometimes this is not given. This is not given sometimes. Or it's impossible to find the formula of the function. That's the most situation that we encounter when you model the situation. We don't know the function, but we kind of know how to measure the instant change of the function values, right? So for example, we are projecting the future, right? You cannot just go to the future and then come back to past, right? Impossible. So you just make your measurement in a small period of time. Like say 1 year is a small period of time, short time period, considering you're trying to project into the thousands or 10,000, right? It's just small changes in your time, and you take the measurement, and you find the difference, whatever the value you're taking measurement, the climate or whatever. So then what you want to do is you want to make it as a differential. So we take a small change right now, okay? I want to see what this change causes in after a long period of time. So we only want to see if I make a change this small at this current state, and what's the result at the end. What's the output is going to change. How does the output going to change? So this V is going to the kind of a meaning of the change of your output, and this is your change of your input. So if you make it more conceptually, your differential is a map that assigns the change of your input into change of your output. That makes sense? Your function is actual assignment of the value of the point from in the domain space to the value of the point in the codomain space. But the differential that derived from the function is the map that sends the change of input to change of output. So you're not looking at the definite values, you're looking at the changes. How much you change will cause how much changes in the output. So everything is kind of, so what we're doing here is not arbitrary change. We are estimating the change in a linear approximation, in a linear way, because all we are trying to make as a change is a linear thing. So we are making a vector. So vector is just a line, right? Vector, if you vectorize everything, it's just making it into a line. So linear change, we want to see how the linear change of an input causes a linear change of your output. That's the whole idea of the differentials, or calculus, or any the business in the integration and the derivative. So that's why I think it's the most important part. Even for integration, it goes back to the differential thing. Okay, so let me just give you one more wrap up, and then really, this is really going to be the last thing that I want to say here. So in the video, I mentioned about some notation to understand this meaning of the differentials. I just want to recap this. So df is kind of a map that sends u to v, where u is the changes in input. But now I can say the change. So and let's kind of make a notation this way. So u, v, x, y, z. So in the beginning I said x and y as a symbol for the input space, but change it to u, v space. Okay. So you can understand the mapping with different notations, and usually this is not covered in the other calculus course because it's kind of a notation that appears in the major courses when you major in mathematics. But I think it's very useful, and also this appears many places in paper or other research other than math area. So I think it's important to know. So first of all, so this is the vector. It's nothing to do with the variable uv here, just the notation of vector at 1, 1, and let's say we said this is 0, 1. So instead of writing u as the bracket 0, 1, I'm going to write this way: 0 times del u plus 1 times del v. Okay, 0, 1 is actually the coefficient of these two things. Okay. Actually, does anyone have seen this kind of notation before? I mean, not in the partial derivative sense, but in the physics. If you go for the physics, then you probably see this notation many times later. But anyway, so and then now what was the v? What was the resulting change? The 1, 1, 3. So instead of, so this is the vector at, what was it? So 2, 3, 5. caused by the change u, and that was 113. So now I'm going to write it as del x 1 times del y 3 times del z. So it's kind of a tricky thing, tricky business here is, but what I want to say, what I think it's kind of useful to understand the material that we're going to cover later, such as chain rule, is that if you look at these two vectors, then you should think that this is somehow identical. So of course it's not the same vector because these two vectors lie in a different space and in a different point. But these are related, right? So the only reason why we obtained V is because we used U as a change of our input. And also, in some sense, you can go opposite. Sometimes if you change your output, then you can change your input by input function. So you can consider this U and V almost as the same thing, right? So, I mean, the one that I can give you an example is that, let's say you're making a joystick here, so you're using a 2 lever here, and then you make a robot to move, okay? Your robot has 2 arms, okay? And that robot is doing something here, lifting balls or whatever, right? So you can either control the robot directly or you can control your joystick. But whatever you do, the output is same. So what I'm saying is that you're moving the lever here is U, and controlling the robot arms is kind of V. So what I'm saying that U and V are the same, kind of same, is that it doesn't matter if you really want the final thing, that it's whether you bypass some other system that uses joystick and then go through this way, or just control the robot directly to get the result. So U, V could be considered the same way. It's considered as the same thing here. So in that case, let's think about this way. So I'm using the derivative again. So what happens when I change my input into, so here, look at this one. What happens, and what does it say is that if I change my input into V direction with the unit speed, then this is how much I change. Okay? This is how much I change. So if I change del V much in my input state, so the joystick, so in some sense, let's say this is my del V, this joystick is del V, this joystick is del U. Okay? So then the robot arm is moving in 3 dimensions that way. So del X, del Y, 3 times del Z. Okay? So now let's suppose that we change my U into one direction of U with the unit speed 1, but not changing V. So I'm just using my second joystick here and then not changing anything here. So then what? So in that case, I'm multiplying 1, 0 here, so I get 1, 0, 2, right? So then this del U is almost the same as just having del X plus 0 del U and del Y, so I just omit this 2 times del Z, okay? So what's the nice thing about this is now you don't have to think about the matrix anymore. Let's say I'm moving these 2 joysticks in simultaneously. So I make change of my first joystick, U joystick, into one direction, and then I make at the same time the change of the second joystick, joystick V, in the twice as faster than the U joysticks. Then this, and then I want to know how much the robot arms is moving accordingly in that case. So then you can just plug in these things together as if it's just these things are numbers, right? So again, I'm calling it as a thing, but it is actually, this is a vector, sorry. So, but I don't want to go deeper into the concept, so I just call it thing. So U is their X to their Z, and 2 times their X, their Y, 3 their Z. And what happens here? 3 times their X plus their Y plus 5 times their Z. So when I do this, by looking at this formula, I know that when I move my joystick U and V simultaneously this way, then I know the robot arm will change in this direction at 3, 1, 5, right? And this kind of symbolic notation is nothing but the matrix multiplication or vector addition, but it gives you nice intuitions when you try to understand the chain rule in the next chapter. So I explained everything in the video, maybe slightly differently because I'm not, because I don't remember exactly what I said there, but I tried to understand. I mentioned this. I know that for sure. So watch the video next time, before you come to the next time Wednesday.